Okay, so we're going to do our next lesson now on the unit circle. Keep in mind, we've already learned about this before. We started talking about this before the class cancellations, but I did want to go through it one more time again just to make sure that it's completely fresh and that we understand what was going on with it. So today's plan is going to be we're going to introduce the unit circle, which, in case you've forgotten, is a circle centered at the point 0, 0 that has a radius of 1. And we're also going to talk a little bit about why it's important. We're also going to deal with special triangles and the unit circle, so we'll connect how special triangles actually relate to the unit circle here. Then we're going to determine the exact value of trigonometric ratios, sine, cosine, tan, with both degrees and radians. All right, let's get started. So first of all, we're going to start with a circle on the Cartesian plane. Remember, the Cartesian plane is just a grid, like an X and a Y grid, where you have an X-axis and a Y-axis. My first question here is going to say pick any coordinate on the circle, so pick an X and a Y, and I want to ask you what relationship exists between X, Y, and the radius of the circle. You can pick whatever X and Y you want in this circle. Personally, I see this one right here as being pretty special. Notice this appears to be at the point 3, 4, so the coordinate to that would be 3, 4. So we know in this case X is 3, and Y is 4. But the question also is, what's the radius in this kind of question? If we drew a line from the center of the circle to that point that we put on the edge of this circle here, we're actually going to notice that this is our radius. But our radius is going to be the same no matter where we draw the line from, as long as it's coming from the center of the circle. So a line drawn from the center of the circle to the outside of the circle, regardless of where you're drawing it, is still going to give you your radius. So therefore, you can see from 0 to 5 right here that the radius is actually 5. Now, as for this whole relationship piece, what relationship exists? If you draw this as a right triangle, the relationship hopefully becomes a little bit more clear. Notice this X component is 3 units long. This Y component right here would be 4 units long. And then your radius up here is, of course, 5 units long. Now, the relationship that exists between them is one that you would hopefully be familiar with from back when you took Math 10, if not even earlier than Math 10. It's Pythagoras, right? So Pythagoras would tell us that x squared plus y squared, in this case, equals your radius squared. This is true for any circle that you have centered at the coordinate 0, 0, right? Your x coordinate squared plus your y coordinate squared is going to equal the radius of your circle squared. And just to check, in this case, we had 3 squared plus 4 squared equals 5 squared. Well, 3 squared, of course, is 9. 4 squared is 16. 5 squared is 25. 9 plus 16 is, in fact, 25. So the relationship does hold true on this question, right? The number one important thing to get from this, though, is this x squared plus y squared equals r squared. That is actually the equation for all circles, right? As long as it's centered at 0, 0, which every circle we're going to look at least in the short term, will be. So the unit circle. A unit circle is a circle centered on the Cartesian plane with a radius of 1, right? So this is where we're not dealing with larger circles, just the radius of 1. So therefore, from what we learned in that last slide, the equation of a unit circle would just be x squared plus y squared equals 1 squared, right? Because the radius is 1. 1 squared is kind of silly to say, so we could also say that this is x squared plus y squared equals 1, because 1 squared is 1, but whatever floats your boat. Now, unit circles are really useful because they're scalable. This means that any relations you find in a unit circle will also apply in any other circle with a radius of r, since that circle is r times bigger than the unit circle, and therefore its coordinates will also be r times bigger. In a little bit more clear English, because you have a radius of 1, if you had another circle with, let's say, a radius of 3, every relationship that you saw in that original circle with a radius of 1 will be multiplied by 3 in the circle with a radius of 3. So for example, the coordinate 1/2 root 3 actually lies on the unit circle, x being 1/2, so about right here, y being the square root of 3 over 2. So this is 1/2 square root 3 over 2. In a circle with a radius of 7, the coordinate would become 7 over 2 and 7 root 3 over 2. So in other words, each of these coordinates were just multiplied by 7 based on the original unit circle. So unit circle serves as a really good reference for coming back to that. Next question, determine the coordinates of the point on the unit circle whose y-coordinate is -√3/2. So in this case, you could draw a picture to help you out. I don't know how much it would help you out, but I'll do it anyway. I'll try my best to draw a circle here. That's about as good as I can get with this, computer pen thing I've got. The y-coordinate is -√3/2. That's going to put us down here somewhere, right? This would be -1. So we're almost at -1. We're just a little bit further down. So our points on our unit circle are either here or here because it's at this -√3. That's a 3/2. So your coordinates are either here or here. If we're looking for the rest of our coordinate, I should say, really what we're looking for is our x component of that coordinate. You can just draw both of these points on the unit circle as being triangles, right? So you could connect it with a line from the center for both of these. Make a right angle using one of your axes. I'll use the x-axis in this case for both of these. And then recognize that this vertical component, this side right here, has a side length of -√3/2 on both of them, right? Now, if we're looking for x on both of these, the one thing that we kind of have working against us is all three sides, right? In order to use Pythagoras, we would have to know at least 2 of the sides to solve for the missing side. The good news is, though, we were told that this is a unit circle. Remember, a unit circle is defined as a circle based at 0, 0 with a radius of 1. And the radius, like I mentioned earlier, is just any line that connects the center of the circle to the outside. So notice when I drew this diagonal line here and here, those would both actually have a measure of 1 because the radius of this circle is just 1. Since we know 2 of the sides of each of these triangles, we can then solve for the third missing side, x. Let's focus just on this one, the one on the right here first. So I could say x squared plus y squared, which is -√3/2 squared, is equal to the hypotenuse, or in other words, our radius, 1 squared. If we start working this out, you're going to see that x squared plus -√3/2 squared is -√3/2 times -√3/2. I'll write that out actually just so it's a little bit more clear. -√3/2 times -√3/2. This will equal 1 squared, which is 1. -√3/2 times -√3/2, just multiply the tops together and multiply the bottoms together. This is going to give us x squared plus -√3 times -√3 is actually going to be +3. You could also think of it as being +√9 because you're just multiplying the radicands underneath the root signs together. So √3 times √3 is √9. √9 is just 3. That's how I got that. Over 2 times 2, which is 4. This equals 1. Let's get x squared all by itself by subtracting 3/4 from both sides. If you took 3/4 away from 1, you're just going to be left with 1/4. So x squared equals 1/4. And then to finish this off, you just need to square root both sides to get x totally by itself. So x is therefore going to equal the square root of 1/4. To square root a fraction, I personally like square rooting the top and square rooting the bottom. The square root of 1 is just 1. The square root of 4 is 2. So therefore we know x equals 1/2. But wait, if you look at this unit circle we drew, if x is +1/2, that's just this triangle. We need to also worry about this triangle. But the good news is we've kind of already solved it. When we square rooted in this step right here, you need to remember that when you square root a number, the answer could be either positive or negative. So in other words, we could have x equals -1/2, right? And the reason this works is because imagine if we went in reverse. Remember, to go in reverse, we want to get back to an x squared, so we would just have to square both sides of this. X squared is literally just x squared, but -1/2 squared would be -1/2 times -1/2. -1/2 times -1/2, of course, is just +1/4. So it still brings us back to this 1/4 that we had started with. So these two are your possible x values. Since it's asking explicitly for coordinates of the points, we can actually more correctly answer this question as saying the coordinates would be 1/2, -√3/2. That's one of our coordinates. And then our other coordinate would be -1/2, negative root 3 over 2. So that would be our other coordinate. All right, next question. Is the point negative 1/2 on the unit circle? Well, to answer this kind of a question, let's go back to what the formula is for a unit circle. The formula for a unit circle is x squared plus y squared equals 1 squared. Or in other words, x squared plus y squared equals 1. To check if this is on the unit circle, we just need to check if these numbers satisfy this equation. Remember back a few slides ago, I looked at the one where it was x is 3 and y is 4 and the radius was 5, and we checked and it certainly worked. 25 is equal to 25 on both sides of the equation. That's the same idea what we're doing here, okay? So just plug in your x and your y into the equation for a unit circle. That's how we test to see if a point is or is not on the unit circle in the first place. Anyway, let's start throwing these in. X being negative 1/2, we'll say negative 1/2 squared plus y, which is positive 1/2, so positive 1/2 squared. We want to see if this equals 1 squared. Let's not fool around with that. 1 squared is just 1. There's no reason making this more complicated than it needs to be. Negative 1/2 squared is just negative 1/2 times negative 1/2, and that would give you positive 1 over 4. Plus 1/2 squared is just 1/2 times 1/2. That would also give you positive 1 over 4. And we're going to say that's equal to 1. Well, 1/4 plus 1/4 is equal to 2/4. 2/4 equals 1, or in other words, 2/4 is 1/2. 1/2 equals 1? I don't think so, right? Clearly that isn't true. What I like to do is go back and make sure I say these are not equal all the way up. So we can answer this question by saying, no, it is not on the unit circle because it does not satisfy the unit circle's equation. If these coordinates don't make this equation become correct, then it's not on the unit circle. The same strategy would work if I'd asked you, is this point on a circle with a radius of 7? Well, then you would have just tried x squared plus y squared equals 7 squared and then see if it works, right? This case though, no, it certainly did not. Okay, arc length in the unit circle. What was the relationship between arc length and the angle measured in radians? We actually talked about this just during last class. Arc length, of course, just to remind you, on a circle, arc length is just the portion of the circumference by which an angle covers, right? So if you had an angle right here, let's say that's our angle, angle theta, then this section right here, this whole section I'm trying to bold, that would be your arc length. Now, the arc length is actually related to your angle, but it's also related to the radius of your circle, okay? And the relationship, as we found, is that arc length equals your angle times by your radius, but only if this angle is measured in radians. If that angle was measured in degrees, it's not actually going to work like this. You'd have to convert that angle to radians before you do this formula. This formula is on your formula sheet, by the way. It's up in the top right-hand corner. On your formula sheet, though, they've rearranged it for some reason. They say theta equals A over R. This is the exact same thing. It's just they divided by R on both sides, and that's how they got it. But your arc length is your angle times by your radius. Now, the way I always remember this is understanding what a radian represents in the first place. Radians, of course, are related both to your arc length and to your radius. Your arc length is just your radian measure times by your radius itself. So in other words, your radian measure, your theta, in other words, is actually just telling you how many times bigger your arc length is than your radius. So radians is how many times bigger your arc length is. I'll just say A. Your A is compared to your radius, R, right? That's all that radians is representing. So on a unit circle, what can we conclude about the length of the arc subtended by the radian angle theta? So in other words, what can we conclude about A compared to the radian angle theta? Well, again, if A is theta times R, on a unit circle, R is 1, so we can just say your arc length is your angle. So in other words, on a unit circle, your arc length, this portion of the circumference, is actually equal to whatever angle you have, as long as that angle is measured in radians. So that's another good significance of a unit circle. It's very convenient in that regard. So for an example, determine the length of the arc subtended by an angle of pi over 2 on the unit circle. This kind of goes, in relation to exactly what I was just saying. You can use your formula if you really want to go crazy with this. A equals theta r. We're looking for A. We know theta is pi over 2. That is in radians, so that's good. And it's a unit circle, so r is 1. Well, clearly then, A equals pi over 2 times 1, or in other words, A is pi over 2. That's it. That's all that question was asking. Moving on. So special triangles. In Math 20-1, we often use special triangles to help us express certain trigonometric relationships in an exact value. Basically, all they were really used for was to make it so that if you had either a 30, 60, 90 triangle or a 45, 45, 90 triangle, you didn't have to worry about having decimals for certain relationships, right? So if I asked you like, oh, what's cosine of 30? Instead of giving me some horrible decimal number, you could just actually tell me an exact value trig ratio, so in other words, a fraction that made it a little bit more exact. So there were two situations we had these special triangles. Like I just mentioned, there's the 30, 60, 90 triangles, as you see below, and the 45, 45, 90 triangles, as you see below here. In Math 20-1, we gave these to you. In Math 30-1, we don't. We expect that you understand how to build them yourself. The only key difference in Math 30-1 is we don't like using the ones where the hypotenuse is some weird other number, because what we want to ultimately do is connect this to a unit circle. That's a terrible looking unit circle, but I'm trying. Anyway, on a unit circle, of course, let's say you had 30-degree angle, like right here. Let's say that was 30 degrees. Your hypotenuse isn't going to be 2 like it was as we learned in Math 20-1. Instead, it's going to be 1, because the radius of a unit circle, no matter where you draw it, as long as it's coming from the center of the circle, is just going to be 1. So this isn't any good. The old unit circles the old special triangles that we had back in Math 20-1, they're not going to work the same way. But the good news is, like I mentioned earlier, unit circles are scalable, and it works both ways. If we want this triangle instead to have a hypotenuse of 1, logically, we just need to take this hypotenuse of 2 and divide it by 2. So if I chop that down in half, that gives me my hypotenuse of 1. Then I have to chop all of these other sides down by half as well. So in other words, instead of 1, we now have this side being 1/2. And instead of root 3, we have root 3 over 2. Last class, I actually showed you how you could generate these. Basically, the idea is we know our hypotenuse is 1. We know we have 30 degrees and 60 degrees. You could use sine and cosine to solve for the missing sides. Ultimately, that would be a lot of work doing that every single time. So this is actually one of the things you're probably going to want to remember. The way I always remembered it was in a 30, 60, 90 triangle, the side across from 30 degrees is 1/2, because 30 degrees is 1/2 of 60 degrees. That's not really a rule, like it's just something I just use to come up with something that helps me. That's all I got, right? It's easy enough to remember that the hypotenuse is 1 because we're dealing with a unit circle, but understanding that the side across from 30 degrees is 1/2, that's at least a start, because 30 degrees is 1/2 of 60. That's just how my brain works. That's how I like remembering it. As for this root 3 over 2, that's kind of a big mess. There's not really a good way of remembering it, at least not that I know of. You could use Pythagoras to solve for it if you knew these other two sides. Ultimately, though, try to focus a little bit of energy in remembering what that side length is. Now, if we move to the 45, 45, 90 triangle, likewise, its hypotenuse is not 1. So let's divide all the sides by its hypotenuse. This time it's a weird number, it's root 2. So let's divide all the sides by root 2. If we divide root 2 by root 2, it gives us the 1 that we're looking for. And then the other sides we can divide by root 2. So we have 1 over root 2 and 1 over root 2. Now, just a weird thing in Math 30-1, oftentimes we don't like having a square root in the denominator. So how you fix that is you just times something with a square root in the denominator by that denominator on both the top and the bottom. So I'm going to multiply both the top and the bottom of this fraction by root 2 and root 2. This is like multiplying by 1, because root 2 over root 2 is just 1. So we're not changing the value of this, we're just changing how it looks. Because again, for whatever reason, we don't like having a square root in a denominator. Anyway, long story short, 1 times square root 2 would give us root 2. And then on the denominator, root 2 times root 2 would be the square root of 4, or in other words, just 2. And the same goes for this guy. It's just going to be root 2 over 2. So just realize in a 45, 45, 90 triangle, sometimes those two sides can be written either as 1 over root 2 or root 2 over 2. Those are the exact same thing. All right, so special triangles in the unit circle. We're coming to a close here, don't you worry. Suppose we didn't know anything about special triangles other than they occur in 30, 60, 90 triangles and 45, 45, 90 triangles. Determine the side lengths of each special triangle using only your knowledge of the unit circle. I'm going to tell you what, because we did this last class, I'm actually going to skip this. The only thing I'll tell you is, let's say you had your 30 degrees, right? So this is about 30 degrees. It's not perfect, but I'm just kind of eyeballing it. We know the hypotenuse is 1. You can use sine and cosine to solve for your x and your y. I'm not going to lie to you guys. What I usually do is when I realize that I have a 30-degree angle, even if I forgot that whole dumb rule that I told you guys about a minute ago where I said, oh, across from 30 degrees, it's 1/2. You can do this visually. You can tell by looking at a unit circle, as long as you know what all those little side lengths were, like what we covered. I'll just go back real quick, like what we covered on this slide, all of these little side lengths. You can actually tell what's going to be what. Notice when I drew a 30-degree angle on this unit circle here, as a special triangle like embedded inside of it. Notice that your y value is approximately, and again, I didn't draw it super accurate, but that y value there is approximately halfway up, right? It shouldn't be a surprise then that we can say that y is 1/2, right? As for x, that's where you just have that big problem. You got to realize that that adjacent side is going to be √3/2. Again, I don't have a good way of memorizing that, but it's just something that's going to be on you guys. Likewise, if I drew, let's say down here I drew a 60-degree angle, or I should really say a 60-degree reference angle, right? So let's say this part right here was 60 degrees. I guess a 60-degree reference angle would be 180 plus 60, so it's actually 240 degrees, but you get the idea. Notice that this coordinate right here on the unit circle, in case you have forgotten, it looks like in terms of x, it's about halfway between 0 and -1. That's not a coincidence, right? That side length, this x side length, would be -1/2. And again, it's negative because it's on the negative side of the y-axis here, right? As for your y value, it's going to be that really bulky, horrible √3/2. But of course, because it's going down, it's got to be -√3/2. So again, I'm going to skip determining using only your knowledge of the unit circle, blah, blah, blah. What I'm just trying to get at here, what's probably a little bit better use of this slide, is understanding that you can visually inspect your unit circle by drawing at least reasonably accurate angles here. I just eyeballed this. 30 degrees, that looked like 30 degrees to me, it was good. 60 degrees, that looked like 60 degrees there to me, it was good. But you can use a visual understanding to actually figure out what your coordinates would be along your whole unit circle. So you may have noticed in the last example, if we had actually done it, your x value is your adjacent side to your angle. Since the hypotenuse is 1, this means that cosine equals x/1, or more simply, cosine theta equals x, okay? That's a really important thing to understand. Your x value on a unit circle is just cosine of your angle. Your y value, likewise, is the sine of your angle, no matter where you are on your unit circle. So these relations exist in all quadrants. The cast rule, which remember said C-A-S-T, the cast rule told us in which quadrants each of our trig ratios would be positive. Cosine is positive down here. All of them are positive up here. Sine is the only one that's positive here, and tan is the only one that's positive here. But that cast rule helped us understand which trig ratio is positive or negative. Question is, why does that cast rule work? Well, if we understand that your x is your cosine, notice down in this quadrant, the only thing that is positive between your x and your y is your x. So x is positive down here. X is positive and y is positive in the all quadrants. So in other words, both cosine is going to be positive and sine is going to be positive, and therefore tan is also going to be positive. Don't worry about that right now, though. For this quadrant up here, the only thing that's positive is your y, right? And again, sine is y, so that's why sine is positive up here. Tan is the only one that's positive up here because if you think about it, x is negative over here and y is negative. Now, tan, if you were to draw a tan, of course, of an angle, is your opposite side over your adjacent side. So tan is the only thing that's positive here because your opposite side is your y and your adjacent side is your x. And a negative divided by a negative is going to give you a positive. So that's why tan is positive down there. So the cast rule, even though we didn't go into super big detail back in Math 20-1, there is a reason why that rule exists in the first place. And it is because your x and your y's are related to your cosine and your sine. X is your cosine, y is your sine, at least when you're on a unit circle. So connect the unit circle to trigonometry. Determine the exact value of the following trig ratios. Cosine of 30 degrees. It's probably best just to draw your special triangles right off the bat. We can assume that this is on a unit circle, so we have a hypotenuse of 1. This is 30, this is 90, this is 60. Remember, across from 30 is your 1/2, and across from 60 is your crazy √3/2. Cosine of 30 degrees on a unit circle, right, is going to be your adjacent side divided by your hypotenuse because of SOHCAHTOA. Okay, cosine is adjacent over hypotenuse, so adjacent is this side divided by 1. You might as well write that all out. √3/2 over 1, which is of course just √3/2. Okay, sine of 60 degrees is going to be opposite over hypotenuse. Well, sine of 60 degrees in this case is also going to be √3/2. Tan of 60 degrees, on the other hand, is your opposite divided by your adjacent. So we're going to have a little bit of work on this one. Opposite is √3/2 divided by your adjacent side, which is 1/2. Now, we don't like dividing fractions, so we keep change flip, keep the first one, change it from a divide to a times, and then flip the second fraction. This is going to be √3 times 2 over 2 times 1, or in other words, 2√3/2, which simplifies down even more because those 2's cancel to be just the square root of 3. Next one's a tough one, tan of 225 degrees. If we drew on a circle where 225 degrees is, that's a horrible circle again, but you know what, bear with me. 180 degrees is here, 270 degrees is here. That means 225 is somewhere in between. And if you do the math, you're actually going to see that 225, which is about right here, is going to have a reference angle coming off of your x-axis as being 225 minus 180, which is 45 degrees. So that's a special triangle in itself. Let's draw a 45, 45, 90 triangle. Not exactly the best there. You know what? I'm actually going to fix that up. I can erase things here. So you know what? Why not do things a little bit better? There we go. That's a little bit nicer, at least. It's not perfect. My hand is pretty shaky on this pen that I'm using on my computer, but you know what? You get the idea. On a 45, 45, 90 triangle, hypotenuse is still 1. The other two sides of that weird one, it's another one you'll have to remember. It's √2/2 and √2/2. So tan of 225 degrees is really like saying tan of 45 in quadrant 3. Well, tan of 45 is going to be opposite over adjacent. So in other words, it's going to be √2/2 over √2/2, which of course, since you're dividing the same number on the top and the bottom, that's just going to equal 1. And we know it's going to be positive 1 because of our cast rule. Tan needs to be positive down in that quadrant. Last question here, cosine 5π/6. That's of course a radian measure, right? Let's still deal with radians though the same as we usually would. Just to remind you, oh, that's not very straight. Just to remind you, we have the same relations exist with radians as they do with degrees because it's just a different measurement system. Keep in mind that 180 degrees is actually pi radians. So 5π/6 is just under 1 pi. 1 pi would have been 6π/6. So we know we're just under 1 pi. So let's say we're just going to say we're about right here. If we want to deal with that as being our right triangle in the corner here, then we're going to have a reference angle in this bottom corner. Let's figure out what that reference angle would be. We know our true angle is 5π/6. We're not quite at pi. If we want to find a reference angle here, we just have to go pi minus 5π/6. This isn't very useful when you're subtracting fractions that don't have the same denominator. So let's give this pi the same denominator by putting it over 6 and putting a 6 on the top as well. That makes it a little bit more clear. 6π/6 minus 5π/6 would just give us 1π/6. That's going to be our angle, right? Now, 1π/6, you might remember from last class, is actually the same thing as 30 degrees, right? And if you didn't know that, remember you can always convert back to degrees by timesing it by 360/2 pi, okay? Don't worry about that for now though. Pi/6 is the same idea as 30 degrees. So in other words, we're going to use this same special triangle as before. Since we're looking for cosine of 5π/6, and that reference angle is pi/6, of course, cosine is adjacent over hypotenuse. So in other words, cosine 5π/6 equals the adjacent side, which is √3/2, divided by our hypotenuse of 1. So cosine 5 pi over 6 equals root 3 over 2. But let's just watch our cast rule. Notice we would be in the sine quadrant, so this really needs to be negative root 3 over 2. That was a very messy slide. I apologize, but hopefully you can follow. Cosine 30 was this, sine 60 was this, tan 60 was this, and tan 225 was this. All right. So to summarize, we're almost done here. The equation of the unit circle is x squared plus y squared equals r squared. This can be used to solve for a missing x or y coordinate if you're only given the other, so no angle needed at all. It can also be used to check if the coordinate actually shows up on a circle, right? So in other words, if I said, oh, is this coordinate on a circle? Just throw it into that equation there. A unit circle is a circle with a radius of 1, blah, blah, blah. I think you can read that. Special triangles are ways of representing the exact values of coordinates in the unit circle. Yeah, we've already talked about that. And you only need to remember the special triangles for quadrant 1. The coordinates in the rest of the circle are just reflections of quadrant 1. That's another really good thing to take away from this. So in other words, just understand using a combination of your cast rule and just even a picture of what a Cartesian plane looks like, knowing where your x is negative and where your y is negative. That'll really help a lot. Okay. So your task I want you to do for practice is page 186, questions 1 to 6, as well as question 9. Give those a try. Again, if you have any questions, send me an email, send me a remind, post a question on Classroom. You can ask each other for help on this, but please get these questions done. It's useless just listening to these lectures and not actually getting any practice in. Anyway, thanks guys. Again, contact me if you have any questions.